So for lab number 2, we're going to cover standing wave and resonance. The thing that's written in red must be completed before entering the lab. So the next thing we're going to do is observe the sound from 55 Hz to 1000 Hz, and we're going to measure the wavelength for each of the frequencies. I will continue from 6 to 10 so that you can fill in the chart that's needed for the pre-lab and the formula that are also needed to complete the lab. Alright, so let's begin from number 1. So we're going to open up and we'll click on the first one. Alright, and you're going to click run now, and you'll have to do this in the lab as well. It will take a bit of time loading, and let me just move it over so you can see everything. Okay, so we're going to start from as instructed 55 Hz. Now you can use the up down cursor on your keyboard, so I'm just going to go up to 55, there we go. And as you can see, the wavelength is much longer. Now just to give you an idea of what it sounds like, I'm going to turn on the sound, and there we go. Okay, so we can't really seem to hear anything. Let me turn my speakers. Right. There we go. Okay, so that's 55 Hz. So that's just basically saying that there's 55 cycles per second. Now if we increase it to 110, let me just click here. Alright, so I clicked, and let me try that again. So I click and I move it up to 110. And then we can increase it to 440. It just takes a moment. And you'll notice here the wavelengths are again shorter. And to save time, I'm just going to go all the way to 880. And that's doubling the frequency again. And as you can see, the wavelength is shorter. Now, the pitch is probably getting to you, so you might want to turn that off. And we're going to click on measure. Alright, now notice how it says it's in meters. This makes sense because obviously we're not going to be able to capture 500 frequencies in a second. And same thing with the measurement, the wavelengths are actually quite long for a very, very low frequency, and 500 Hz is actually quite low because once you get outside of the sound spectrum and you get into X-rays and UV rays and gamma rays, the frequencies are in the thousands and thousands, if not millions. Okay, so the way to do it is to place your, well, I think the best thing to do is to press pause, which is on the bottom. So let's do that. Okay, so you're taking the measurement from 0. Notice how 0 is not at the end, and then you can take it from the middle of the darkest band to the next part where it's the darkest band, so that's one whole wavelength, so it looks like 0.75 meters for this one. If you increase the frequency, if you decrease the frequency, you'll notice that the wavelengths are getting longer, yes. And so you can take the measurement from 2 bands. This time I took it from the middle of the white band from one point to the other, so it looked like 0 to 1.8 meters. So it's 1.8 meters for a lower wavelength for that scenario. But you guys have to do it for those 5 frequencies just listed right there on the page. Okay, so the next part is we're going to answer question number 3. So what I did is I went to physics, classroom, standing waves. This is a pretty good website. If you just click on the first one right there, it will take you to this part and I'll show you an animation. Now you can read about it. In the animation you'll notice that the blue wave is moving to the right and the green wave is moving to the left. This is kind of like an echo or a feedback, and when this happens then you get like a resonance. That's the whole point of a resonance, is the maximized amplitude. You'll notice that the black wave is bigger than the blue and green wave. And you'll notice that the black wave is not moving at all. In fact, in the middle, where it says AN, it's increasing its maximum point and decreasing to its maximum point. But if you look where it says N, N is where it doesn't move at all in the black wave. It's fixed. It absolutely doesn't change at all. And that's what happens when you have two waves, whether they're longitudinal or transverse wave. And when they're colliding to each other and they have the same frequency, they produce nodes and antinodes. You can read about it right there to answer these three questions. So please go to that website. Okay, the next part is we're going to find out question 4, which is about resonance. Type in Wikipedia and resonance. I'm not a big fan of Wikipedia, but in this case I think it's fine. Go and click on the first one, and you can read about the first paragraph. It says in physics, resonance is basically where you have maximum oscillation, and as you saw in the previous example, two waves were colliding into each other, producing a maximum wave that was much larger than their original wave. If you want to see a real-world example, you can see here the video is taking a while to load up, but basically this is an example of resonance that happened in real life. This bridge had the same frequency as the wind, and the whole entire bridge had the same frequency. It wasn't structurally designed to have different structural support to counteract a particular resonance. So if you look in this video, on the left hand side where the arrow is, that's where the antinode is. That's the maximum amplitude, a maximum displacement, both negative and positive. But if you look where the yellow line is, that's your node. That's where there's barely any upward or downward movement, and it's very similar to the wave that you saw earlier. So that's an example of how this actually applies to real world, and you have to consider this all the time when you're designing buildings, even high rises in Mexico City. You have to take this into account when there's an earthquake. So this is why this is kind of important and relevant. Just to make a side note, frequencies are not just about bridges and design, it's also about everything that's around you. Everything has a frequency. Your body has its own frequency, your brain has a frequency, your eyes have its own frequencies. And we're not talking about beats, we're talking about how it resonates. Your eyes, it's about 70 hertz, and I think your general body is about 6 hertz. Anyways, onward to the lab, this is what I have to say. You're gonna have a tuning fork, and all you gotta do is turn on the FET program, and once you turn it on, it's the same one that you saw earlier in the lab. You're gonna strike this against the ground, or against the table. Alright, so you strike this and then you change the volume using the up-down cursor. Alright, so as soon as you have something that's in tune, then you can write down the hertz. So right now I have it in tune. If you want to actually hear it, that's the same one. So here we have the question for the lab, which is basically determining the length of a closed air column that will resonate for a particular tuning fork frequency. That's the whole point of the lab. These are the material that you have, and just below that you have the prediction. As I scroll down, you'll see prediction before we move on to procedure. Okay, so now we have procedure, and here we have a cylinder on the left, which is what I will demonstrate shortly, and this is the table that you must copy for the lab. The procedures, don't worry about reading it right now, just copy down that table, and the first row with the 2 columns right there, those are the ones that we're going to solve experimentally using the lab. Everything else will have to be done mathematically, and I'll show that below. So, and this column is going to be a frequency that's not 512 hertz. It's going to be the frequency that you determine using the tuning fork, because it's not labeled and we have to find out what the exact frequency that is resonating at. Okay. Alright, and these are the formulas that you have to write down for the lab on the right hand side. This is the first resonant point at quarter wavelength, and then the one below is 3/4 wavelength. I want you to draw the diagram with it as well, so that you understand that at antinodal point, that's when you're going to have resonance. And the bottom one is 5/4 wavelength. You're going to need all 3 of these formulas, 1/4 wavelength, 3/4 wavelength, and 5/4 wavelength, to help you solve the rest of the chart mathematically, because we're only doing the first row experimentally. Okay, thanks. So here we have a tuning fork, and this is something you can use to strike it. So let's try again. Okay. Alright, so it's right about there. Now what you want to do is you want to measure it. So you take a ruler and you measure it. And after you fill in all the chart, we have the analysis and evaluation, which you can start working on after you fill in the chart in the lab. And that can be part of your lab report for your discussion and conclusion. And that pretty much sums it up.